This is the way we are managing this type of meeting. Please put all of you in mute your microphone, and we will do the presentation. Then write the questions in the chat, and at the end of the session, I will read the question for the professor. Maybe now we can start. So thank you for all of you to join this webinar, this DevHub webinar. I'm really happy to see all of these people connected. We are already 120. The webinar is related to the software engineering in the era of cloud computing and machine learning. And in this webinar, the Professor Hong Zhu, could you put in mute, please? And will explore how the evolution of the software engineering paradigm, and will focus on the thanks to this new trend of cloud computing and machine learning. A few words about Professor Hong Zhu. He is a professor of computer science in the Oxford Brookes University in Oxford, UK, and he is the chair of cloud computing and cybersecurity research group. His research interests are in many areas, and of course focusing on software development technology, AI, machine learning, but also software design, testing, programming language. And he has a very huge list of paper, also in journal and international conferences. He's a senior member of IEEE and British Community Society, so very active in the academic world, and he was also a member of the academic board of the Technology Council of last year in the software track, and in particular in software developer, automation and quality. So, but let's stop me to talk. I will give the microphone to Professor Hong. Just a reminder, since additional people joined, please put your microphone in mute. We will do the question and answer at the end. Put your question in the chat. I will read at the end, and then the Professor Hong will answer. So it's your turn.
Thank you very much, Giovanni. It's my great privilege to be here to share my views on the current state of art in the development of software engineering, and also to share with you my vision for what is the direction we are moving to in the subject area of software engineering. And also I will share with you very briefly the work we've been developing in the past 10 years or so, based on our previous experience as well. The work with my colleagues, my students, and also more widely with my friends in the area of software engineering. We all know software engineering is rapidly developing in the past decades or even longer. And we always see people have two big kind of events that happening in the world. One we call the cloud computing, which extended to fog computing, edge computing, Internet of Things, which I believe it is very much linked to your company, ST MicroElectronics. And so I will also cover that area. And another big storm happening in the world is machine learning. Now, I believe everybody have engaged somehow in the machine learning, trying to use, for example, ChatGPTs, and a lot of surveys in the recent 2 years, and to see machine learning being widely used by the industry. And one survey says the end of year 2023 and the beginning of 24 says that more than 90% of developers in the IT industry is using machine learning in their work and also after their work, outer work. And more controversial data says that the 75 developers benefit from the machine learning, but on the other hand, also nearly 40% of programmers say they don't trust the machine learning. So what is going on in these two active fields? My understanding is we are experiencing a kind of a paradigm shift that started even earlier. And if we look at how traditional software engineering is done to compare with how cloud native applications like the SaaS software as a service developed by the big companies, we found that there is a fundamental change of software engineering practice on almost every aspect. So from architecture, which are moving from the client server, the so-called web plus n-tier kind of monolithic architecture, and to the microservices backed up by big data technologies like NoSQL databases, the search tree, and the process as well changed from originally we start with the waterfall and it changes to agile methodology kind of process, and then now people are engaging in so-called DevOps and continuous integration and continuous testing, continuous delivery kind of process model. Although it has the kind of principles linked to Agile very much, but this is a completely different thing from the organizational point of view. The project management, for example, we traditionally have the kind of split of development into smaller teams of separate different roles, some for business analysis or requirements analysis, then to the architects, programmer, testers, and then we have operation teams. However, now we are having smaller teams, much smaller teams. Each team owns a bunch of microservices as a part of the whole big system with millions of different microservices. And we look at the job market. It's often we see the call for staffs of so-called full stack developers. So it's not divided into different roles. You need to do everything from requirements to the operation. Then quality, we are concerned with different things. In the parts we're talking about mostly in the teaching of software engineering, reusability, maintainability, testability at the search tree. But now we are talking about more important things on the scalability, horizontal scalability, for example, reliability, fault tolerance, response times, quality of service, cost efficiency as well. And the kind of quality assurance teams have become the so-called part of the each microservice teams. And the tools are different. The traditional kind of testing tools like XUnit, for example, JUnit, and the GUI-based testing tools, Selenium, Mercury. Now we are teaching students Docker, Kubernetes, and also a bunch of tools which has not existed before for the software engineers, like cluster monitoring, log analysis tools, all these kind of things. Configuration management, like GitHub, is still being used for different teams, but people are not using GitHub the same way nowadays. The most important software life cycles has been changed from the kind of version-based evolution. We have 3 weeks or 6 weeks of a release every new version. But now we have a continuous evolution in the form of ecosystem. So what is happening in this? In 2018, we studied the phenomenon, and then we argue that the shift from the kind of traditional software engineering to the cloud native software engineering is a paradigm shift. First of all, people might ask, what is the software engineering paradigm? Is that the same thing as we in the science kind of paradigms? I would say, philosophically speaking, they are very, very the same thing from their nature. So what is the software engineering paradigm? We can define it as a consistent set of software development techniques and methodologies guided by a philosophical model of computing. Here I would like to emphasize the philosophical model of computing underneath all these development techniques binding together. So this kind of a model is an abstract model of a computer system, including hardware and all the software running on top of the hardware. And this kind of a model indicates how the computer, especially software applications, should be constructed and how they should evolve. And it's the glue binds the set of techniques and the methods together. This is very important to recognize the philosophical model of computing and then to understand how we should move forward. It is essential for any paradigm to be well established, to have a good understanding what does it mean. For example, in the past, we had several software engineering paradigms already. Starting from the beginning, we had the machine code, assembly code, and then moved to the first, maybe you can call the beginning one is a version 0 paradigm, and then structured software engineering in the second. And this is the first well established kind of paradigm called the structured software engineering. The model of this, the philosophical model for this paradigm is we view the computing as a processing of data, where the data are stored in the computer system in the form of taps or the kind of external storage, and also when it's processed, it's loaded to the memory. And here the computer, we have the von Neumann computer as the main architecture model. And the software, therefore, in this kind of a model, software is a collection of procedures or routine operations, they processing the data. They are organized in hierarchical structure. So this is what the kind of main characteristics of the first generation of paradigm. The second paradigm is object-oriented. We all know this kind of software engineering paradigm, and it is still widely used in the industry. And we are most developer trained in this paradigm. So the philosophical model for this is different from the structured software engineering. Now, we consider computing as interactions between objects. And the hardware could be a network of computers rather than just one von Neumann kind of architecture. And here the software, because of philosophical model, the software is a collection of computational entities, which is essentially the objects. They are the kind of entities encapsulate the data and the operations together. Rather than in the first model, we see the data and the program is considered one is a passive, one is active, but now they encapsulate together. But the objects themselves are instances of classes, and they are passive. They are through the evocation to control one another in that way. Now, if you look at in the history, there are two candidates to the object-oriented software engineering paradigm. And one is called logical programming in the 1980s, proposed by Japanese based on the kind of logical programming. So this is the paradigm. Another paradigm at the same time is called functional programming. Logical programming consider computing as a logical inference, and functional programming consider computing is a functional application to the data. The functional programming coming back now, especially like Python, is very popular. This is another story we're going to look into later on. So if we look at microservice or cloud native application, so what is the microservice? This is important to understand what is the new paradigm in the in the cloud native kind of application development. So microservice architecture, from the software architecture point of view, we look at what are the components, what are the connectors, and how the system are configured. So for microservices, the components are services, which means the component runs on its own process and they are independently deployable. And each service is specialized in one function, and the whole system is have a fine granularity, consists of this kind of services. So this kind of microservices is in small size. That's why it's called a microservice. And to be a complete system, we need a larger number of them, especially larger number of instances of microservices, as well as the larger number of types of microservices, the templates of microservices. These kind of components are connected through service request and response, through a very lightweight communication facility. For example, most popularly using RESTful APIs to connect them through the kind of TCP/IP and HTTP kind of protocol. The most important thing is microservice architecture, which distinguish it from the traditional, well, we wouldn't call it traditional, the previous kind of paradigm. You could call it a service-oriented computing in its configuration. First of all, the most important character of microservice is dynamic, which means a service or instance of a service can be dynamically created and terminated. The second feature is duplicate. This is also different from service-oriented computing. It is the components or the microservices can have multiple instances for each service if you need. And the third feature of the microservice is the service can be distributed to a cluster of machine freely to where you want to put it. So this is the main feature of a microservice architecture. And this, when we have the microservice as the basic concept, basic building blocks of software engineering, then we have a new paradigm. In this paradigm, we can see the hardware is much, much more complicated than previous kind of enterprise computing kind of software engineering. It has clusters plus internet to form the so-called the cloud. But this is not just the cloud native applications. Cloud native applications combined with mobile devices, for example, mobile phones and so on, to deliver the service to the user. And more importantly, it penetrates to the Internet of Things. And as a kind of optimization of this kind of cluster, mobile device, Internet of Things, then we have the fog edge servers and so on. The software is a collection of this kind of microservices instances, plus the kind of container images or Microsoft templates to form a dynamic ecosystem of microservices. They have the three kind of configuration characteristics, 3D, dynamic, distributed, and duplicated. And the philosophical model now, if we understand how the microservices to work together is collaboration, is not one controls another. And you see the kind of torrents is happening to enable the kind of system to be reliable, which is why it loses the connection between them to be collaboration rather than control. So to put it simply, in this microservice paradigm, the philosophical model can be summarized as computing is collaboration between active computational entities through service requests and responses. Here we must emphasize, first of all, the old programming languages, the kind of a based software engineering is mismatched with this philosophical model. And another thing we must emphasize, microservice as a terminology is widely used in the industry to mean two things at the same time. One means the microservice instances. People also call them the agents. They are agents in a way. They are independent on their own processes, can be deployed, and so on. Another thing microservice also used to refer to the template or container images and so on. But they are actually similar to classes in this sense. So we invented a word called cast to be similar to the notion of classes. So cast is the classifier of agents, and also there are templates of agents can used to generate the instance of microservices. But for a paradigm, we notice that if we consider the microservice as a new paradigm, then it's a mismatch with the old programming. However, we don't have a new programming language which matches the philosophical model. And this is important for a paradigm to have its full power. Like we have Pascal, C kind of programming language to realize the structured software engineering power. And for the object-oriented paradigm, we have Java, C++, C#, this kind of a programming language which enable object-oriented software engineering become a practical, more powerful kind of paradigm. But for the microservice, the kind of a new paradigm, we don't have such a programming language. One of our research in this context is to develop a new programming language called COPL, which is using the microservice as the building block, and it's specially designed for the kind of microservices. So in this kind of language, we have the cast as the something similar to class, but it is for the instantiation of service microservices called agents. And for example, here we have two casts. These two casts can be compiled separately, and each of them can be independently deployed to a cluster, whichever the order you like to do. And they don't need to be linked or whatever. They just compiled and deployed. And then you can create instance for these two casts, the agents, to execute on different machines and so on. You can create them using command line, like we start a new program, but also you can write the code like a list cast to create them on different machine in order you like to. And then the instances of these casts, the agents, they dynamically link together to communicate and so on. This is the kind of things we did in this paradigm. The second thing we did is we developed and proposed a concept called integrated development and DevOps, development operation environment for the microservices, which support the development, deployment, and execution of the program in COPL. So this is the kind of interface we have for the coding part. It can be used as a plugin to the Eclipse, using project management facilities and so on. Also, we can link to the GitHub. And then, the most importantly, in this environment, we have the two integrated together to manage the cluster. Directly, you can operate the cluster and also have the tool to deploy your cast to different machines. And then you have a tool to support the execution of the agents, to monitor their executions, to create instances, and also very importantly, we have the debugging facility. The debugging facility is reported in this paper. I will not do talking too much about it. Essentially, it supports the remote debugging of microservices in a dynamic way, which means the microservice is running normally as a program on a machine, and then if there is something you suspect something goes wrong, then you can get this microservice into the debugging mode and see how it works and what is the problem. And you can go to multiple different microservices on different machines remotely to debugging them. This is the kind of things. Now let's move to the second paradigm. The second phenomenon we have, as I mentioned at the beginning, machine learning is increasingly used in computer applications. And there are challenges to develop this kind of software with machine learning components. And also, more importantly, the challenges to develop the components, the machine learning components, how to apply software engineering principle, develop them. So far, a lot of technology being developed as a subject of machine learning, especially AI, for how to develop these kind of models and so on. But if we want to develop these kind of models as a daily business of software engineering, there are lots of challenges. Especially, we started focusing on the quality assurance and testing of machine learning models. And at the same time, the machine learning technology offers new tools to support software engineering. Especially recently, we have the large language models, which you can apply to many tasks of software engineering and explored by many researchers in these directions. We'll share what we do in this part as well. So we can, lots of people already say the machine learning application to software engineering to develop software is a new paradigm. But let's speculating, what does it look like as a new paradigm? Looking at the theory, we study the paradigms. First of all, there are two parties we use machine learning or develop machine learning for the software engineering. First of all, is we develop the kind of spatial machine learning models for spatial requirements to be used in software in software applications. And the second kind of phenomenon in the paradigm is the use of large language models or other general purpose machine learning models. We tailor them to achieve specific goals. These are two approaches to use machine learning models. And for different approach to the machine learning models used in application, there are a number of different things happening. One is, first of all, the machine learning models that have different architectures in addition to traditional different training methods, training algorithms, or people call them machine learning algorithms, like using decision trees, random forest, logistic regression, support vector machines, and most importantly, deep neural networks. Deep neural networks start to have architectures inside the neural networks as well. So the development process will often need to define the architecture, select the right model. But however, this process before that, we have feature engineering. We have data collection, data cleaning, feature selection, and feature representation design, and all these kind of things before we design the machine learning architecture. And after we design architecture, then we have training and then the performance evaluation. This is how we do for the machine learning models we develop. This, we can see a bunch of new techniques, new concepts, and they are completely different from the traditional software engineering. So in this sense, we are in a new paradigm. That makes sense. Now, for the use of large language models, we found in the past couple of years, a bunch of new technology emerging. For example, the fine-tuning of machine learning models, foundation models plus additional layer to specialize. And also we have the so-called prompt engineering. And more recently, we have the so-called RAG technology, retrieval augmented generation, the SUA. Now, in this kind of mindset, we found it's different from what we traditional software engineering based on so-called the computational thinking. Now, people talking about data-driven. But the philosophical model here we can see is different from what we see in the past paradigms. Here we think of computing as knowledge extraction, especially from data. We how to using the data to get the kind of a component. You can call it knowledge or function. And second, you apply the knowledge to your instances as a knowledge application. This is what the computation in this kind of paradigm. And the quality concerns, even for the using large language models, it's the same. For the fine-tuning, you need the data, and for the prompt engineering, you need to consider what is the context and so on. RAG, especially what is the local knowledge or the context being stored in the vector database or whatever. So that is also considered computing is knowledge extraction and a knowledge application. Especially like a prompt engineering is how properly to apply the knowledge become the key issue. But from the software engineering point of view, we can see the quality attributes, the critical quality attributes is shifting from what we say, the scalability and so on, although they are still make a lot of importance here, especially for large language models, but we are more concerned with the performance in terms of accuracy, recall, precision, and so on. And very importantly, we found robustness become a big issue because neural networks has the kind of adversarial example problems that damage the robustness, because robustness is the measure how the machine learning model generalize from the data to the knowledge. And robustness manifests its importance in terms of fairness, safety, trustworthiness. And trustworthiness is another thing when large language model has a hallucination problem, become a hot topic in the machine learning research. So this is the kind of paradigm we can see from the current state in the development. In this context, we develop a new software testing methodology, trying to implement the kind of need to meet the requirements to test machine learning applications automatically. The traditional method like XUnit and Seleniums, they are not working well for the machine learning. We need a new method. Our method is called datamorphic testing. We consider testing as an engineering problem, and especially a systems engineering problem. So to test these kind of applications, we need to build a test system. The testing is an engineering process in which we develop a test system. And we use this test system to operate the test system to achieve the testing purpose. And the test system evolves with the system under test to achieve the testing efficiency and effectiveness, because the machine learning model is evolving many times, retrained many times, and so on. So the testing system is a system which supports testing activities and managing test resources. There are a lot of benefits for this kind of test systems to be explicitly specified, defined, and implemented. We can apply the kind of software engineering process in these test systems. How can we organize a test system which suitable for the machine learning? So we consider such a test system should be best to be a kind of system which consists of a set of test entities and a set of test morphisms. So test entities are objects or data which is used and generated in testing. For example, test cases, program the test report, documents, and all these kind of things are entities. Test morphisms are the kind of mappings on test entities, and they generates and transforms test entity. For example, test case generators, test oracles, adequacy metrics, report generates, and all these kind of things are morphisms. The morphisms can be implemented as code and be evoked and so on to achieve test automation. It is what actually people does in machine learning. We write test code to evaluate the performance and so on. Now, if we look at it more widely, what kind of test morphism can we have? We found a lot of things under this kind of the categories, especially test executors, test metrics are particularly useful, but most importantly, in the machine learning, most important concepts are seed makers, which get seed test cases, and data morphisms transform data from one to another. Metamorphisms, we check the correctness of the test result. We found they are particularly useful for the machine learning. For example, we have lots of pictures. We want to have a machine learning model which is recognize what is in picture, the flowers, what kind of flowers. And we have loads of pictures, but just using this benchmark is not adequate to test the machine learning models. So we need a method to generate more this kind of data to test the machine learning models. For example, here we have the data morphism, which removes the background color. And then when we test them, we can easily define the test oracle to check if they are correct by comparing the flowers. Are they identify the same flowers? And we can find lots of these kind of data morphisms to test machine learning model adequately and automatically. And we also developed a tool to implement these kind of things. In this paper, I'm not going to go to details. If you're interested in using this tool for your work, please feel feel free to contact me. I'm more than happy to give you the free access to the tool. And in this tool, a test system is implemented a kind of a Java class. The entities, so test entities are implemented as attributes, which you store the data, and test morphisms are implemented as methods, so you can operate on attributes. The main function is the kind of tool can support the management of test system and to achieve test automation at 3 levels: activity level, strategy level, and process level. We have done case studies with the face recognition. For example, for original picture, we can have a number of operations to change the face attributes, and then to get lots of different pictures and test the machine learning model. And we can see in our case study with a bunch of industry face recognitions, we found they have the kind of robustness issues, but generally speaking, it's not too bad in face recognition. And it shows how this test can be automatically conducted. And we also applied this methodology to testing classification of applications. In these 2 papers, give them more details. We know the application for machine learning, a large proportion of the application is in the form of classification problem. For example, face recognition is to classify who is in the picture, and object recognition is also classification, and disease diagnosis from the pictures, from the blood samples are also classification problems. But traditionally, how do we test classification type of software? We usually select test cases on the borders and then slightly off the border in order to detect if the border implemented is correct, if there is particularly if there is a shift error or the notation error. But for machine learning, we don't have the clear defined border. If we borrow the ideas, we found it's difficult to apply the theory of software testing to this kind of problems. So what can we do? So we implemented automated exploratory testing to find the boundary between the classes. If you're not familiar with exploratory testing, you can see the 2 books. They are very good in this topic. So the kind of face recognition kind of testing we do is so-called confirmatory testing. We know what is the correct answer and we check if correct. For exploratory testing, the general idea is to discover the information, the features in your software. So it is a different strategy. I'm not going to discuss too much of it, but just to mention that we can automate these using datamorphic testing methodology by defining a test system for how you're going to explore the software, and then design and implement exploratory strategy in the form of algorithms. The algorithms always test the entity and test morphism as a parameters, and then you can evoke the kind of algorithm to do the exploration. And with this, we can prove the algorithms are correct, exploratory is complete, and then to execute the strategy to perform tests. And for example, for this kind of classifier, if we build different machine learning models, if you evaluate them in terms of the performance, they are very similar. But when we found the borders between the classifiers using our exploratory test system automatically, you will find the machine learning models all different shapes. This is the original one. The classification is the original one. The border, theoretically speaking, should like this. This is the neural network, decision trees, This is the voting, hard voting, K nearest neighborhood, KNN, and Lisa logics regression. It's just a straight line, and all of them are different shapes. And with that, we can define a new matrix to distinguish them, which is using the idea for the border. Now, the theoretically correct border is a no, and typically for machine learning is not no, but using the exploratory testing, we can find the border like this and what is implemented, and then you can measure how far the distance from the theoretical one to this implemented one using our metrics. Another problem that we addressed is after you testing machine learning model, you don't know how to improve it. This is a methodology we proposed and also implemented in our test cases. I will skip this. We're running out of time, so I skip this. And we can improve this. And for the large language models, we see at the beginning I mentioned it is widely used by programmers, and we have working on this on how should we test these kind of tools. This is a survey for what is done in a research on machine learning in the AI community, and we proposed approach to this by a new benchmark with metadata from software engineering point of view, and we found the larger language models have different performance on different subject of coding, starting from 90% to very poor at just above 50% of correctness. And when the complexity improves, the performance goes down. And this is for all different subjects, the performance goes down when complexity. And we also proposed a method for user-centric evaluation rather than just run on benchmark. And that is a process model to mimic the kind of use of a large language model in the real use from software engineering point of view. And we found the situation is much better. So finally, just take 1 minute. What's the direction for future development? We believe the kind of a cloud computing machine learning will inevitably merge together to become what we call the intelligent service-oriented computing paradigm. In this paradigm, we can see the kind of characteristic here. The software is going to be called a multi-agent system with multiple different machine learning models combined together with traditional service. And the hardware, we have all these kind of things plus GPU, and the philosophical model is moving towards we consider computing as a knowledge extraction from data and the knowledge application through knowledge exchange and collaborative problem solving. The process tools and the quality attributes, all these things is going to be rapidly developed in the future, but I think the basic idea is here. So that is the idea we would have. I'm sorry for a bit rushed. I understand it's a big topic and I'd like to share with you. Thank you very much, and questions, please.
Thank you. Very, very interesting presentation. There are some questions in the chat, so please post your question in the chat. I will read and ask Professor Zhu to answer. So, hello, Professor. My work is most often done in memory with executable and the script, shell script, Python script, being executed in the command line, obviously in a monolithic architecture and OOP. Would be our go-to paradigm, but do you think a microservice-based architecture could be beneficial in our use cases?
Good question. Thank you, Giovanni. It is the active research topic, I believe, in the research community, to moving the boundary from the cloud to the fog and the edge, and eventually go to the Internet of Things, to the microcontroller kind of the thing. It is branded in the keywords called cloud continuum. It is very, very important to benefit from the power of microservice to the application with the Internet of Things and so on. This is, I think it's very important. Now, why the progress is slow? It is, my understanding is, the current technology to implement microservices is based on container technology plus container orchestration technology, specifically the kind of things that Docker plus Kubernetes. But that is a centralized management of microservice with the cloud as the boundary. Your Kubernetes cannot penetrate the boundary from your cloud to the fog, to the edge, which is owned by different people, and then to the Internet of Things, which the scale cannot handled by the Kubernetes. Now, my solution I would like to offer is a new paradigm of programming, new paradigm programming language, a novel programming language like a COBOL. In this kind of language, we are not relying on the kind of middleware. The middleware, it has to be run by something on top of existing system. That if you are dealing with the scale of Internet of Things, so to the security concern, to break security concern between the cloud and the fog and the edge, there is a problem for this middleware getting more complicated. So the logic, currently microservice has a problem of logic complexity because of the massive scale of concurrency. And that is dealt with partly through the fault tolerance technology, especially when the instance of microservice crashes, you simply remove it from the system, isolate it and remove from the system, and then to create a new instance somewhere else, not on the same hardware, and then start fresh. And because of multiple instances, so the whole system is still working on. That is the current way we're dealing with the complexity, try to make every microservice simple, but the whole system could be more complicated. But there is a problem for this to be penetrate to the Internet of Things. The COBOL language has the advantage for you can static analysis the logic across the different agents, different casts. And also you have the freedom to run them on different machines. Now, I did my experiment to using not microcontroller, but very, very small device like Raspberry Pi. And that can penetrate from the boundary. And I create my own small distributed lab at home using retired notebooks and PCs, and also a cluster on Google Cloud to be one system running my code of COBOL in this environment. That I tried to break the kind of a boundary between the cloud and the fog and the edge. So that's the kind of things that I would offer. It should be a good idea to do so. That is that's what I say, the power of cloud native paradigm. The microservice paradigm has not fully realized if it's fully realized, it will further revolutionize the software engineering. Thank you for the question.
Thank you for this. There are several additional questions. We have 4 minutes left. We have 4 questions at the moment. What do you think about the testing approach proposed by you for safety and security software?
Yes, good question. The safety and the security testing has been a hard topic for distributed computing. The methodology in the current testing, especially test automation, is based on the kind of JUnit to test the unit level, and the Selenium on the surface level, on the interface level. But security and safety is more difficult because it's more linked to the real world. That is partly the methodology we proposed for the datamorphic testing. It's applicable to these kind of things will benefit. For example, we are using the testing for the, I didn't go to details in top, but I mentioned there for the autonomous vehicle to test the image recognition in different weather conditions and in scenarios, the safety rates scenarios. That is the kind of things to, especially safety testing. You cannot test it in the real world for high risk kind of situation like autonomous driving. You cannot test it. You need an emergency brake. So we can test it in a datamorphic way to argument to change the data in a safe situation to a safety critical situation and test it. It will improve test efficiency. Security as well, you can apply context morphisms, data morphism to implement the security scenarios to test them efficiently. That is the kind of thing we are doing experiments at the moment, for example. Yes.
Okay, thank you. Another question. We have 1 minute. Are there any plan to migrate the C IDE into the cloud IDE?
Good idea. I think that to make it a cloud IDE would be a very good idea. It's what to say, to have a server running on the cloud and have a web interface, and that could be a good idea. However, we don't have the human resource. It has been taking me quite a lot of effort to develop the code, and my team as well. We had spent a lot of effort on that, but it will be interesting to do that, and it will be very useful as well to have this kind of tools to be implemented as a cloud ID. Yes, it's good if we have resource, and I'm more than happy to collaborate with you to make it to happen.
Okay, so we have 2 questions linked to the philosophical model. What do you think about the philosophy and development in a serverless paradigm? Is it a step forward for microservice architecture? And then another one, when you refer to philosophical model, are you referring to a particular philosophical approach? Moreover, when you speak about morphism, do you refer to the group of theory?
Okay.
So one is the serverless paradigm, so a step forward.
Yes. We refer to approach. Okay. Morphism is a terminology borrowed from algebra, including group theory, but is more general to the category theory, general algebra, the kind of concept to represent the kind of general mappings and transformations of data. It's the kind of a new approach to the test automation problem. You can say this is a philosophical model underneath the testing methodology we developed for the machine learning, and it is also applicable to the traditional software as well. It's not just for the machine learning. So it is the kind of conceptual transformation as the system view for the philosophical model of the data morphic testing. Yes, I think that's a good point to look at my own methodology of data morphic testing to consider what's a philosophical model. It is a very important part of that, yes. Another question I can see there is about whether morphism applies to continuous function. Yes, it's of course I think yes, but mostly the test morphism are meant to be the kind of the activities you can a unit activity you perform during testing. You identify them and implement them. They can be coded, script, and then evoked to perform test automation. And this kind of test morphism can be combined, composed as a parameter of algorithm to form test strategy. Now, in the traditional software, we have the strategy have to be executed by human beings. Now, in this kind of system engineering approach, it can be implemented algorithm with test morphism and test entity as the parameter. And this process can also be recorded and then replayed, edited, and replayed many times to perform experiments. Like in machine learning, we do lots of experiments and then to check the performance and so on. That can be done in a process level. So the automation is not just write to one test and execute it. We can combine them as a system approach. That is the philosophical model underneath our testing methodology. Thank you for this question and the inspirational question. Thank you.
Okay. So maybe Lily, do you want to conclude the session? So thank you, Professor, for this very interesting and inspiring presentation. So Lily,
I think perhaps there is one question left.
last, yeah,
Last one. Yeah. Otherwise, we can ask Professor Zhu to answer offline, but 3 minutes more, and we can answer to Omar Siala.
Accuracy of
I
machine
see
learning.
there is a question about serverless paradigm.
Yeah.
Serverless paradigm is not actually, I would not say this is a paradigm in a way. It's more a technology, because for paradigm, we want to have the kind of more complete set of technology. together with the processes and so on. Now, serverless is addressing one particular problem in cloud-native application, which is the kind of provision operational complexity in a kind of a big, larger scale cloud-native application. If you think of serverless, the couple language we implemented, we don't need to talk about server at all. We have the kind of just running on top of Linux or Windows, whatever the operating system, it doesn't matter. We don't need to have the kind of packaging and the kind of concept at all. So this is a technology, a type of middleware which supports the cloud native application. It's an alternative to Docker and Kubernetes, but with less concern of the infrastructure issue, but wrapped into a technology to support it. I don't think that is the right direction to the microservice, especially to solve the problem that microservices are now limited to the cloud side, but moving to the fog age. There are experiments to do this, but there is a big barrier because the middleware could not go to the kind of a control of the fog. Serverless will be more serious, more difficult to move, to break the barrier. Especially you go to the number of Internet of Things, more microcontrollers in your system, it will be even harder to achieve that. So I don't think serverless would be a paradigm shift. It is more technology solution. Yeah.
Okay.
Okay.
Yeah.
Okay. So we can close here the session. And thank you to everyone in the audience for your active participation, and a special acknowledgement to you, Hong, for sharing your vision with us. As we wrap up today, I'd like to take a moment to remind everyone about our upcoming webinar on May 6th. This is Giovanni's moment to shine. Giovanni will be joined by Stefan Biermann from GitHub and Camille Cligenois. I hope I spelled the name correctly. To present the GitHub action.
GitHub Copilot.
Copilot.
Yes. Yep.
Copilot, and I think you won't want to miss this opportunity. So thank you again, and have a nice day.
Thank you. Thank you. It's my great pleasure. Thank you.
Thank you. Bye-bye.
Thank you. Bye.
Bye-bye.
Thank you.
Oh, there is a question about sharing the slides. You have my slides, Lily?